Hello. This, let's continue with the second section of the part one introduction unit. Last time, we explained the meaning of interleaved execution, parallel execution, and a concurrent execution. We also mentioned a very important example to show you that when a program is doing this input-output, its execution has to be suspended. Not only this, from this example, we'll learn two important concepts, concurrent sharing and the mutual exclusion. Then we talk about the concept of concurrency, which was started in operating system design and then developed into multi-programming and then multitasking or multi-threading, so that a program execution could also be split into multiple pieces and run in a concurrent way. We demonstrate the ampersand operator to run a program in the background. As a result, you are able to run multiple programs at a time. At the same time, one of them in the foreground, the remaining are in the background. Then we're going to talk about something even more interesting, because when we do background process running, these processes or programs are independent of each other. That is, they don't need any help from each other. That is not very interesting. So the next part is, let's do just a little bit cooperation between two processes. So all the previous examples have processes running independent of each other. They don't need any help from each other. They are the so-called independent processes. If processes must communicate with each other to complete a task, they become cooperative, or we call them cooperating processes. For an example, suppose you and I are two processes. We work together in order to get the job done. So somewhere in my process, I have to use the data or the result you computed and deliver it to me. So we have two situations. When I reach that point, and if your result is already there, my program will run fine. But what if when I reach that point and your program hasn't get the result done and put into that location, what would happen? The value I retrieved would be a garbage. So all the subsequent computation would also be garbage in, garbage out. So in this case, what we really need is synchronization. What does that mean? Now, we don't need to know much. We just use the previous example. If you are going to compute some data for me, at a certain point, before I reach that point, I must have some way so that I would be suspended until you deliver your results. So this is one aspect of synchronization. And this is a difficult point when we reach the synchronization components. So be aware of that and work hard for that. But so far, it's no big deal. Remember, when a program runs in the foreground as a process, it has its stdin from the keyboard. and its output would be sent to stdout, which is the screen. More precisely, it's not the screen. It's actually the terminal you open to run this process. So this is what we need to know. Now, let's look at this operator, the vertical bar. You know it in C programming, that is bitwise OR operator. Just like the ampersand operator, we are not going to use this vertical bar in C. Instead, we use it as a Unix command line operator. This operator is referred to as the pipe operator. If A and B are two programs, we write A vertical bar B. The meaning of this writing is the std out of A becomes the stdin of B. Look at this diagram. A has its stdin, the keyboard here, but if we write A vertical bar B, that is A pipes to B, so A's std out is the same as the stdin of B, but B still has its std out. So the meaning of A vertical bar B or A pipes to B is when A prints anything to std out, that output becomes the input of B, because that output is to std out, but std out of A and std in of B becomes the same. So you print out something to here, and B, when it's going to read something from stdin, would retrieve the information and send to B. So this is the meaning of the pipe operator. Now let's take a look at a very simple example. I'm sure you know the argument vector is an array of a pointer ended with a binary 0. argv0 is a pointer to a string, which is exactly the program name. argv1 is a pointer to the string that represents argument 1. argv2 is a pointer to a string that represents argument 2. Here, the first line here, we retrieve argument 1, which is supposed to be a string of digits, a positive number. And this string of digits is converted to an integer by the function a to I. The result is stored in the variable limit. Now keep this in mind. I do not have sufficient space to write all the error checking. So I omit all of this error checking in your program. In order to make it bulletproof, you have to do all the error checking. Don't take it lightly. So after obtaining limit, we print out limit. The first line printed out pa.c is the number read in from argument 1. Then we loop limited number of times. Every time we print the value of I with this edit descriptor to an array. Here we use sprintf. So in sprintf, the first argument is a character array. That is to be used to store the printed out. The remaining two arguments, the first is the editing descriptor followed by the variables you wish to print this value. So this part is exactly the same as printf. The only difference is rather than printing to stdout, we print it to a character string. After this sprintf completes, we print it out with this string adding descriptor. So this program simply iterate limit number of times, where limit is obtained from argument 1. Every time it's just printing a value from A. Say if limit is 3, then we have printing 1 from A, printing 2 from A, printing 3 from A, and so on. So you may want to say, CK, this is overkill. We just move this here and print out the value I directly. And that's simpler and more efficient. Probably CK is not a good programmer, kind of dumb, using two statements to do a simple thing. Well, actually, I have to warn you. I did this with a purpose. When we write multiple processes program, printf could have some problem. You will see it when we reach process programming. So far, just believe me, this is the way to do the business. Then let's take a look at pb.c. The structure of pb.c is exactly the same as pba.c, except that the way of reading input. So the first line, reaching a complete line into the character array input. Now we use get s. This get s function is in the very old standard, the so-called KNR, Kernighan and Rich book. I use it here as an example to encourage you not using it because it has some security consequence. Anyway, let's assume that is okay. So get s would read in the first line from stdin. That line will be saved to input. Then we convert that line, assuming that that line contains only digits and representing a positive number. Convert to an integer and save to limit. Then we loop limit number of times. In each iteration, we use getS again to read a complete input line and then print it this way. So from B, the string we just read in with some indentation. Now again, this is not the right way to print. You should follow the previous example as printf to a string followed by printf. In fact, we are going to learn more about this. So far it's okay because our program is simple. Now, why I discourage you not to use getS? The question is here. We have character array of 100 positions. Remember, each character array or string requires one more entry because we need to end that string with a binary 0. So in this input array, we could only store a string of 99 characters. The 99 plus 1th character is for the binary string, for the binary 0. Now, getS has a very unsafe semantic. You want to getS input into an array, character array. So getS simply reading a complete line, no matter how long that line is, and save into input. Now, if that line has less than or equal to 99 characters, it's fine. You could save into here plus a binary 0. But what if that input line has exactly 100 characters? So that 100 character would be stored in input from 0 to 99. But we need a binary 0 to end that string. Where can we store that binary string? When getS reads this, it simply save the binary 0 in the 100, 101st position. And that one is not in the input array, right? We have a array overflow situation, out of bound. Now, what if you have, say, the input line has 150 characters? Well, the first characters will be here. The next 50 would follow the first 50, followed by one binary 0. So we don't have this extra 51 position to store the input. So this 51 characters would be stored somewhere after this input array, which has the potential to overwrite existing information stored there. This is very risky because the information destroyed by these extra characters could ruin your program execution, could also override some of the existing variables value. So never ever use getS. Now, recall PA1, if the input value from argument 1 is 3, then the first line printed out by PA1 is 3. Then print out printing 1 from A, printing 2 from A, printing 3 from A. So the total number of lines printed out by PA would be 4. Okay, now suppose we compile PA and PB and run it this way. So with PA 5, 5 is for PA's argument 1. So PA and the PB are run concurrently with a pipe operator. It means the output of PA to stdout would be read in from stdin of PB. Now, if I put 5 here, how many, what is the number of total lines output? Well, in the PA's loop, we print 5 lines. Before printing this 5 line, we have a line printing the value 5. So the total number of lines printed out by PA is 6. So get back to PB. If we use pi, so PB would receive this input from PA's stdout. So this getS input would actually get the number, the line with number 5 there. So this 5 would be converted to an integer, saved to variable limit. Then we have a loop that would execute 5 times. So every time we read a complete line. So the first time we read in PA's first output from the loop, printing 1 from A, and then printing 1 from A is here. We add some spaces from B, and the output is here. So the output line from B would be this string followed by whatever it reads in from stdin. Okay, so that line is exactly printing something from A. So in this case, PB would receive 5 from the getS on the first line. Then the second line, PB resin, would be printing 1 from A. The next one would be printing 2 from A, and so on. So when PB gets a line, the first line will never print. So PB would receive this, printing 1 from A. That is stored in input. And that input is used in printf. In the printf, the descriptor would have some space, and from B colon followed by whatever PB resin from stdin. Therefore, PA prints out this part, and PB at this part appended by the line read in from the stdout of PA. Because the value is 5, we print out 5 lines here. Notice that PB never printed out the value on the first line. Now, please stop for a while and go back and study the programs carefully. This pa.c, pb.c are available in the common directory. You should download that tar.gz, unzip and untar and run them. Now, let's do one more. That's pc.c. Instead of using getS, here we use fgetS. This is a much better function than getS. fgetS requires 3 arguments. The first one is the character array to be used to store the input. The second argument indicates the maximum length we can read, including that binary 0. The third argument indicates from where we read in the information into the first argument. So this fgetS input limit stdin means read in one complete line from stdin, but we have only this number of positions in this input array. So because of this bound, the use of fgetS is much better than getS. fgetS would return a value. If that value is not null, it means stdin still has something to be read, and that thing was read in and stored in input. And if fgetS returns null, that means end of the file has reached. Nothing can be read. So we break this while loop. So this means as long as there is something in the stdin, we read in to the input array and print this input array by adding some indentation from C and so on. So this program is even easier than pb.c. Now, if we run this program this way, PA7, so PA's output will become the input of PB. PB's output will become the input of PC. Here, stdin belongs to the keyboard, belongs to PA's stdin. The terminal windows, that is stdout, is the stdout of PC. You never see stdin of PB and never see the stdout of PB because PB's stdin is the stdout of PA. And PB's stdout is the stdin of PC. So your input goes to PA after some computation, sent to PB, and PB does some processing, sent to PC, and finally PC prints out its final results. So here, let's take a look at this part, the output. When PA runs, it will print out 8 lines. The first line contains number 7, followed by PA printing 1 from A, printing 2 from A, and so on. So we have seen that, and PB reads in the value 7 from the first line and get the second line, printing 1 from A, and then add from B and print it out to its std out. So the std out from B is this section. So this line is printed to the std out of PB, which becomes the stdin of PC. So PC would reading this section, which is the output of PB. And then PC at this portion and print it out. So the whole line is printed by PC. And PC add this part to the output of PB. And the PB add this part to the output of PA. So we have a 3 concurrently running program, each of which sends its output to the input of the next one. This pipe operator is very useful in Unix. Unix promoted the idea of small disputing. So all programs are written not very large one. So frequently in the Unix script, you see a whole lot of programs connected by pipes. Let's take a look at an example. If you use PS command to list everything in the system, of course, most of the list of processes are not yours. So your PS here, now you could pipe PS output to a program written by you or by someone else. So what this program would do, just extract your process. That is, the user ID is, the username is you, or you want to extract all processes whose PID is in certain range. So the output of everything from PS is piped to your program. Your program takes the output from PS and screen those unneeded part and only printed out the needed part, and so on. This is very commonly seen operation. For an example, if you know Unix, you probably know the program AWK. This is a very useful program for you to screen out those unneeded information and only preserve the needed one. Now, as we mentioned, PA, PB, and PC run concurrently. To convince you, let's use the PS command. This argument, dash uppercase A, is the one I use on my system. Different Unix variants may have a different way or different argument for you to list all processes. So refer to the Unix manual page for the needed arguments. Now, I use PA 10,000 pipe PB pipe PC. Why I use 10,000? It's because I need the program to run sufficiently long so that when I type PS-uppercase A, I will see all 3 programs. If you use only 10, probably by the time you finish typing PS-uppercase A, the whole sequence is done. So here is a screen output. So when I type this, I find out PA is here, PB, PC. PA receives a PID 27518. The PID of PB is 27519, and PC has a PID 27520. So as you can see, if we run this process for a long time, and you from the PS command, you know PA, PB, PC are run concurrently. So this is a very limited cooperation because PB depends on PA's output and PC depends on PB's output. Therefore, PA, PB, PC are cooperating processes, and their communication is through the pipe. That is, we hook stdin of the next program to the stdout of previous program. This type of communication is very simple, linear, going from the first to the next to the third one, and so on. But still, it is a communication. We will see more complex communication techniques among processes and the thread very soon. Now, let's take a look at some many people would believe ancient command from the Unix shell. The first one is Ctrl-Z. If you are used to Windows or MS-DOS, you know in MS-DOS, Ctrl-Z is the character of end of file. But in Unix, Ctrl-Z has a totally different meaning. Remember, when we type a.out, a.out would run in the foreground. Once a program is running in the foreground, you lost your keyboard to type any command line arguments because the keyboard is associated with stdin of the foreground program. So what if you need the keyboard to issue some command? Simple, you just type Ctrl-Z. After typing Ctrl-Z, the current running foreground process will be suspended. Because the foreground process is suspended, you get the command line prompt back. You could issue other command lines so you can run a different program. But normally we don't do that. That is, we don't run another program in this way. Instead, we normally use the BG command, background. When we type BG return, the system would run the most recently suspended process in the background. Of course, you have to be sure. When that program goes from foreground to background, that program will not read anything from stdin. So here's a sequence of commands. I run my program prog, and then type Ctrl-Z. Prog is suspended, not running, followed by BG. Then the just suspended program prog would resume its execution in the background. The opposite command is FG. The FG command simply brings the most recent background process back to the foreground. So if after that I type FG, my prog program, which is currently running in the background, will be moved back to the foreground. And it has the keyboard as its stdin. You may want to say, why do we need this? As I mentioned to you, these are quite old Unix commands. In the 60s and the 70s, graphics terminal did not happen. So all programmers has a terminal, character-based or text-based terminal. It is able to display 24 lines. Each line has 80 characters. This is exactly the default size when you open a terminal window. So your terminal window is a legacy thing from a terminal usually referred to as VT100 terminal. So you use that terminal, 80 by 24 terminal, for editing, writing your program, so on and so forth. Now, you type in your program and compile it successfully and link them together, and finally you're going to run it. So you type prog return to run your program. Because prog is running in the foreground, your keyboard is for the stdin of prog. You cannot type any command line there. But what if suddenly you found out you need to do something? Well, one thing you can do that is, so far, if you don't know this command, you simply kill that program. In modern days, you don't need to kill that program. You simply open a second terminal window and issue the command there. But in the good old days, I'm sorry, you have no way to do that. So are you going to kill that program? Well, if the program is a small one, killing it probably will do no harm. But let me tell you, when I was a professional programmer, typically my program will run for 23 or more hours in order to get a whole bunch of scientific output. So what if my program has run for, say, an hour? Then I found out I need to do something, to write a report or something, or send an email. I am really not willing to kill that program, because that would extend my program running from 23 hours to 24, probably missing the deadline. So what am I going to do is simply type Ctrl-Z to suspend that program. Then type BG, allowing that program to run in the background. Now, once the program is run in the background, I am free to use the keyboard to type in whatever command lines. I could bring up a word processor to type a letter or a report, or bring up a email program to send email and whatever it is. Or if you like it, you could bring up a game. And I used to do that when I was young, just like you playing game. But in good old days, game are character games. There's no graphics. We can only use the forward arrow key to move and the space bar to shoot. That is it. And for those terminals without the forward arrow keys, we may use W for going up, Z for going down, A for going left, S for going right. So we need the keyboard to play game. Now, if you do not put your program to background, you cannot play game. So after you're tired or finish your work and tired in playing games, you just bring your program back from background to foreground. So these are very interesting, rarely mentioned Unix command. You may want to try it. Even though in today you don't care, you simply open a different terminal window to do your work. So this is the last command I want to talk about. This is a kill command, a shell command. The kill command does not only kill processes, it could do a whole lot more. As we mentioned earlier, when you type PS command, you are able to see all of the running process under your user ID and their corresponding PIDs. To terminate processes, we simply use kill, all lowercase, followed by dash, followed by all uppercase, KILL, followed by the PIDs of those processes you wish to kill. For an example, suppose I want to kill PROG in testing. Then first of all, we find out the PID of PROG, which is 28821, and the PID of testing, which is 28823. Then I issue this command, kill -KILL, followed by 28821 and 28823, return. Immediately, the program or the process corresponding to PROG and the process corresponding to testing are killed. Stop running. You may want to say, hey, I used to put a 9 here. That is KILL-9 followed by 28821 followed by 28823. Are these two the same? Yes. This the name KILL is numbered as 9. Now, this is a short story, although it may take several minutes. I believe in the next unit, when we talk about operating system or hardware support for concurrent computing, we will use this. So listen carefully. I wish you could rewind and listen this part again. Operating system does communicate with your program. The way for the operating system to communicate with your program is through a set of signals. So signals in an operating system are used to communicate from the operating system to your program. I know you probably never wrote a program for that, but don't worry. On the course website, there are a few pages I developed for the operating system class probably decades ago. You may refer to that, but that is for the Unix signals. But today, most people prefer to use the IEEE signals. So there are signals defined in the operating system. Each signal has a name. Each name starts with SIG, all uppercase. So the signal corresponding to killing processes is SIGKILL. This SIGKILL has a number 9. So you put kill here, you are actually saying that sending the SIGKILL signal to these processes. What the other signals? There are a whole lot of it, but because this is not about this type of programming, you may learn from systems programming course. I don't know, but I would like to tell you a few more. Ctrl-C you use very, very often. When you hit the Ctrl-C key, operating system gets your key, press. And if it is Ctrl-C, operating system will send a signal to your program. This signal that corresponds to Ctrl-C has a name, SIGINT, where NINT means interrupt. So if you want to kill PROG and testing, instead of use SIG, KILL, you could use SIG INT. It does essentially the same thing, but it has some subtlety for you to remember. Let's mention it later. So you learn SIG kill, we use KILL. For Ctrl-C, SIG INT, we use INT there. Are there any other interesting signals? Well, I just want to mention 2. Previously, we talked about we could suspend the execution of a process. Can we do that? Probably you don't know that. But if you use signal, you can do that. So that signal is referred to as SIG stop. So if you wish to suspend the execution of these processes, not killing them, you could use KILL-STOP. Now, after suspending some programs, sometime later, you have to resume their execution, right? Otherwise, that program would become a stopped process there forever until the system's down or power off. So the opposite of SIG stop is SIG count, SIGCONT, that is SIG continue. So if we have stopped execution of PROG and testing by KILL-stop, you wish to resume their execution, you simply use the signal SIGCONT. So you put kill-CONT. So this previously suspended process would resume their execution. So isn't it funny? You could stop the execution of any process of you and resume them later. So far, we learned 4 interesting signals: sig kill, sig int, sig stop, sig continue. We only use last few characters here rather than the complete name. So what are the subtleties? First of all, you need to learn the communication from operating system to your program. What does that mean? It means you need to do something. That something is referred to as signal handlers. If you wish to handle a signal, you have to write a signal handler for that signal. And before your program actually does anything, install that signal. So when a signal comes, operating systems simply send the signal to your program. And the corresponding signal handler will be activated to handle that signal. How do you handle the signal? 3 common ways. The first one is the default one. The default one usually means, I don't care, I don't want to handle it. So the system will simply use the default way. For an example, the default way to handle sig-int is terminates the program. That's easy. The second one, you could say, I want to ignore that signal. In that way, you write your signal handler by specifying a parameter indicating when this signal comes, ignore it. But that would have a serious consequence. Suppose in your signal handler, you wish to ignore Ctrl-Z. So when the operating system detects there is a Ctrl-C from stdin or from the keyboard, operating system would send the Ctrl-C to the Ctrl-C handler in your program. Now, if your Ctrl-C handler indicates that I don't care, ignore it, so that means you treated that Ctrl-C key press as it never happens. So no matter how many times you hit Ctrl-C, your program simply refuses to die. You have to use kill. The third way is you write a handler actually do something about that signal. For an example, you write a Ctrl-C handler to do the following. When the operating system detects a Ctrl-C for your process, then a signal will be sent, sig-int will be sent to your process. And if you have a handler for that signal, sig-int, your sig-int handler will be activated. In that program, you could print out a line. Something like this. Did you hit Ctrl-C accidentally? And ask the user to type in yes or no. If the user types in Y, then you go back, return to the normal execution of your program. Because that is an accident. And if the user responds no, then that Ctrl-C is for real, not an accidental one. So you kill the program. Okay? So You could do something like this too. When if your Ctrl-C signal handler is activated, you simply print it up, go away, don't bother me, and return to normal execution. Of course, that's for funny. So you have three ways to handle the signals. Ignore it, or do it in a default way, or you write a handler to do something about it. But always remember, some signals cannot be ignored, cannot be handled. One of them is the sick kill. In other words, when sick kill comes, you have no way to handle it, just your program simply goes away. Hopefully, this would help you to do a bit more in systems programming. I hope you will learn it in the systems programming course. And finally, we quickly go through input-output redirection. I'm sure you know it, probably have used very often. When we write a program, stdin is the keyboard, stdout is the terminal window. But we can always, if your input is so complex, so large, asking you to type in all of input without any mistake could be very difficult. In this case, you could have your input type into a text file. When you run your program, you simply tell your program to read stdin from the text file rather than from the default stdin. By the same reason, you may want to save the program output rather than simply showing it on screen. So when you run your program, you could simply tell the system that the stdout would be sent to a text file. This way, we use less than for input redirection. This means when the program runs, the stdin is redirected to the file data. Of course, if you want to read something from data, then file data must exist before program is run. The next one means when I run the program, PROG, its stdout should be sent to a file called report rather than the default stdin, which is the screen, the terminal. In this case, everything printed out by PROG would be stored in the file report. In this case, the file report should not exist when PROG is run. Now take a look at these two examples. Hope you understand the differences. If process A's output is going to be used by PB, so we use PA pipe PB as we have shown you earlier, but this one would be the same. We redirect the stdout of PA to a temporary file. When this temporary file is established, we run PB so that PB will take this stdin from from this temporary file. So the total effect is the same. PB reads everything from the output of PA. But the major difference is PA and PB in this way, using pipe, run concurrently. In this way, PA and PB now run sequentially. PB cannot run until PA finishes its work, so that the temporary file was closed and file becomes in existence. So these are two ideas. and with same results, but this one is piping, this one is I/O redirection, and this one is concurrent, this one is sequential. Of course, you could use input redirection and output direction at the same time. This slide shows you when program is run, the stdin is from a file called data. And the output to stdout will be saved in the file report. So this ends our second lecture of the introduction part. In this introduction part, you learn some easy things. For example, what is the meaning of concurrent? What is the meaning of interleaved execution? What is the meaning of parallel execution? And you also learned when a program does its input output, its execution has to be suspended until the input output operation finishes. In this example, you also learned two crucial concepts: concurrent sharing and mutual exclusion. You will see and hear this over and over. I hope you remember this magic word and understand it. Then we review some history, telling you that concurrency started very early in the 50s. It was originated in operating system design and then moved into a programming language. In today's modern computer, a operating system can run multiple programs at the same time. Each program, if you know how to do it, could be its execution could be split into multiple threads or multiple processes running concurrently. Then we learn two easy ways to do concurrency. One, the background operator. We run multiple programs at the same time. The problem is these concurrently running programs are independent of each other. They do not do any communication. To show you that you can add communication, we use the pipe operator. The previous program's output could be this program's input, and this program's output could be the next program's input. All of this program run concurrently. Then we'll learn some interesting command. Ctrl-Z, BG, FG. We'll also learn various type of argument to be used in the kill command. We only mentioned 4: seek kill, seek int, seek stop, and seek count. And we also mentioned briefly that these signal can be, some of these signal cannot be handled. When it comes, the effect has to be there. That is seek kill. Some signals can be handled, some or even ignored. And finally, we mentioned input output redirection. So this ends our second lecture. Next week, or our next lecture, will be on the operating system and hardware support for concurrency. Let me stop here and see you next time. Goodbye.